Mr. Arthur, and a little bit of information about my unit plans. I've submitted all of them in chemistry and physics. There were some concerns expressed about the availability of the assessments for the support staff, which would be ELL and special ed, for them to access assessments so that they could modify them. And I also heard some concerns that I'm not sure exactly how to address this, but the concerns addressed were a lack of telling a potential teacher how to implement the unit plan. So I will address that. I'll address both of these in this little talk, and I just saw this one on the suggested panel of the Google Docs, so I'll go through this one. Now, I made my chemistry unit plans adaptable to the mainstream chemistry, which we'll just call chemistry, adjusted chemistry, which would be not a separate class, although that's what I wanted, but it would be those who maybe qualify for special ed, but because of embarrassment about it, they're just put in the mainstream class, and the teacher has to figure out exactly how to handle that, because the grades in that case will not be, with an asterisk on them. So you just have to deal with the situation. You want to encourage the students and challenge them up to what they can handle, but it really amounts to teaching two different classes concurrently, and I have ways that I do that. And then the honors chemistry, they can handle more in a class period. I can handle some more challenging issues to explore. Unit 6, and it's basically about solutions, and we have here standards, and I'm using the ones that are correlated with all the different topics in the chemistry ebook, and that is National Science Education Standards. And they have codes. Here we have Science's Inquiry, that would be A, and A1 would be abilities necessary to do scientific inquiry. A2 is understanding about scientific inquiry. And then we have B, physical science. B2 would be structure and properties of matter. B4 would be motion and forces. B5 would be conservation of energy. And then science and technology would be E. That would include E1, abilities of technological design. E2, understanding about science technology. And desired outcomes associated with these would be to identify the factors that affect how a substance dissolves, describe the equilibrium in a saturated solution, and to describe factors that affect the solubility of a substance. What I think is most useful in a lesson plan that's ready to use is the essential questions, and then you see those there, and it's about everything, different things about solutions. And these are learning activities that can be applied off of this unit plan however the teacher chooses, and these are apps that are integrated into the ebook. I haven't had a chance to go through them yet because I don't have, as a teacher, I don't have a clearance level to set up my class. I tried doing a workaround and I did get my classes set up, but I didn't get them populated. I did put in a ticket to IT, and I just sent an email today about it to Travis, telling him I would like to get set up now. I don't know why they have to put this barrier in front of the teacher for the chemistry ebook, because they don't with the physics ebook. I'm basically set up with the physics. They're both from Pearson, so I don't get it. But the Chem Tutor has these different topics you can see under learning activities, which are beneficial to the students. I mean, I'm sure they would be beneficial to the students. I could show them in class, or I could just leave it up. I could just assign them to the students. And then they have virtual labs, which would mimic the physical labs in the classroom, and they would exercise the scientific process parts of your brain. There's one about boiling water, and another one comparing real and ideal gases, and conductivity of electrolyte solutions, and solutions in general. And just like they have a chemistry tutor, they have a math tutor with some basic skills that are important in chemistry. Graphs, how to read graphs, how to solve equations, and then direct and inverse relationships, like volume and pressure would be inverse to each other, for example. And then converting units, such as between the metric system and the English system, or just the scale of the units, when you're solving equations. So all those are good helps. The teacher can use them in class, or the student can just do it on his own as a sort of a private tutor. And then here's many just sort of, I don't know, would you call them vignettes, or just discussion questions, sort of a mixed bag of teaching things that you can intersperse throughout your lesson. And some are at the honors level, some are more at what I would call the adjusted level, so that everybody's addressed one way or the other. The honors students are challenged, and the lower functioning students are not overlooked. Everybody's challenged at the level that they can withstand, or at the level that they need. There's little experiments you can do, like this one is one. You could do this one under the hood, or you can just read about it here. And there's different activities you can do. Learning activities, I'm not telling the teacher in what order to do them. I'm addressing this unit plan to a graduate of a university in chemistry education, or maybe physics and chemistry education. They've had student teaching, they've had methods courses, content courses. They don't need me to tell them, but I can give them some ideas. Preferred way to mentor teachers. I did the same thing when I was mentoring dietetic students at the University of Florida and Virginia Tech. I had them sit with me, and I would model for them for a few patients, and then I would just find a patient speaking of the dietetic students, I would just find a patient that I think would be interesting for them, give them some background, have them read the charts, and then just go at it and see how they did. And with teachers, I would I would give them these resources, but I wouldn't write out a lesson plan for them. I want to see how they do. I want to see how they put together a lesson plan and how they implement the lesson plan. They can watch me a few times and get some ideas from me, and they probably had some modeling and observation already through field experiences with the university. These are the elements, and you can see some are for the adjusted here. Like for the adjusted, I showed you the honors here. X-ray diffraction was used to determine the structure of ice. It was the same technology that Roswell Franklin used for the DNA. And then they can do extra studying on how this technology reveals structure. Now on the other end of the spectrum, what about the adjusted? They may have trouble with this concept of electroconductivity of solutions. In addition to dissolving an ionic compound will dissociate into ions in water. So you see it's two different things. Think of table salt. If you dissolved, just stir in some, nobody would do this, of course, but let's say into a glass of water, and you would dissolve a teaspoon of salt into that, it wouldn't it wouldn't disperse into molecules of salt. That is sodium chloride molecules. It wouldn't do that. It would split all the way down into sodium ions and chloride ions. And since the chemical unit is sodium chloride, but the unit found in the water is separate sodium and separate chloride, we don't say that it just dissolved, it also dissociated. Might be a fine distinction for them, so you would want to spend some time on it. And the fact that it dissociates into two charged particles into the water, it's more conductive than is if you mixed a molecular compound as opposed to this ionic compound. But if you mixed a molecular compound such as sugar, it would not improve the conductivity. I would say, if anything, it would retard it. So what you can do is you could have them dissolve some sugar and then some salt, and then test the conductivity with just wires and battery and a meter or a light bulb for each. So these are all some talking points or things you can show the student, just an assortment of things. And the teacher that gets this unit plan can just use this as a bag of ideas, because they already have the ability to structure a lesson. But this would just give them some ideas and leave the creativity up to them. I wouldn't want to go into a school and have an administrator tell me, impose that I must teach in this manner, teach this content at this time. I know what the content is that makes up a chemistry course or a physics course, health course, other kinds of courses, and because that's my field. And each teacher develops its own methods as long as the students are learning what they should learn. Then that's the idea. And then the vocabulary here is where the ELL teacher might have some ideas of how to approach this, how to approach these. These are all the significant vocabulary words that are specific to this unit's topic. here for all the sections of the chapters that come under the solutions heading. These you would call the objectives. The outcomes expressed in is student behavior. So you see describe, interpret, define, identify. They're all cognitive skills. But in chemistry, there are also psychomotor skills, such as operating analyzers. If it's a hospital lab, then you'd have a lot of automation. They can't afford to have people just sitting on a workbench mixing things and so on. But in the lab, you're doing it more hands-on, so you're more closely connected with the reality of the activity. It's not hidden behind a stainless steel cover with all kinds of solenoids and capacitors and things like that, computer circuits that have been developed over years and years. It's more like the original chemists, where they can appreciate the underlying processes more than if it's all programmed. You dispense a sample on one end and get a readout on the other. It's good for you to be closer to the process so you can appreciate it more. This is still more objectives. Remember, this is for a unit, not just a lesson. More objectives. And here, the big units for the chemistry are the chemistry text and a companion series of videos and worksheets and laboratories and so on from Georgia. Georgia must have felt that they had a teacher shortage of science teachers, and so they wanted to give them some help. And so there's a role for the central dissemination of these lectures and teaching aids, coming probably out of the University of Georgia or someplace. But there's still a role for the teacher. The teacher acts more like a quiz section or a lab section teacher. And I think that was a good idea. And it helps me because I have not been, throughout my life, I have not always been a teacher, and it helps me to just inject my assets into the situation and let them do some other things that I don't have time to put together quite as well as they do. And this is assessments. The formative means that as the students are working and learning, you're collecting some data from them, like the notes sheets indicate how well they're attending to the lectures and how they're able to transcribe certain parts of it. And then the worksheet tells you how well they're able to apply. So let's look at the notes, an example of the notes. This is their ability to record important points from the lecture, and while they're doing this, they're learning what are the important things, what are the things they should be writing down, and are they able to keep up and record those. A lot of sentence completion, which I understand is a good technique for the ELL student. And then there's a little quiz at the end, an oral quiz. And then I also mentioned worksheets. They have worksheets, which after they have the lecture, this is where they can apply their knowledge. Do they remember the definitions in the lecture? Okay. And Then there's a scientific effect they were supposed to remember. And then different types of questions. And that's formative because it's in step with the lesson. After the lesson, then there is summative, and it may be covering several lessons. Sometimes it's in the form of a puzzle, a mixture of type of approaches. So this unit 10 might not exactly mesh with the topics from the ebook, but there's a lot of overlap if it doesn't mesh. So the questions are not as in-depth as the worksheet questions because it's covering a broader area. And so this goes with the video companion series from Georgia. So that would be summative there. And I was requested to put more summative evaluation in, so I put an assessment from the end of each chapter in each unit. So this unit about solutions and similar topics, it's really, I'd say, a unit about matter, I should say. So I put an assessment from each chapter that went into the unit here. I just did that today from popular request. And I am suggesting that when you open it with Kami, because the fidelity is much better in Kami than it is in Google Docs. And what you're looking at is the standardized test prep. There are a few end of chapter problems that I captured as well with the key, but what I'm focusing on is the summative assessment is the standardized test prep. It has a variety of question types: open-ended, short answer, multiple choice. There's some based on a diagram, a series based on a diagram. And then these are more true, false. And if you have problems with any of these, they are numbered here, and then it tells you what section to go back to check up and reinforce your knowledge. Now, so how could you implement this unit plan? You're just throwing the student to the wolves. They won't have any idea what to do. Not difficult at all. You have the ebook. I'm going to put this on pause a second. Well, there is an ebook. I was going to show it to you, but they're updating. But what you can do is you go to the ebook. This unit covers chapters 13 through 16 on the states of matter, and you can narrate it for them, or you can actually play built-in narration for them and go through the textbook. It seems like that would be kind of unimaginative. Some people would think that because they're going to read it anyway, but the results I've been finding is that a significant number of students do not read the textbook. So you can be a helper there and help them read the textbook. You can narrate it and you can stop it. Just use your own impressions. What would be difficult for you as the teacher? What would be difficult for you in reading the textbook? Obviously, there's some difficulties if the students in large numbers or large percentages are not reading the textbook. You can be a great help for them by reading through it with them, and especially with not all the students, I mean, most of the students in this school are not labeled as ELL, but some people think that because their language of origin, you could say, however you want to phrase it, is still spoken in the home, it puts them at a disadvantage in reading and listening and writing. So I think it'd be a great help for the teacher to go through the ebook orally with them and try to anticipate what some of their problems are. Just ask questions as you go along. See if even if they don't answer out loud, if they're embarrassed to answer out loud, at least prompts them to think, and just go through with them, go through some of the model problems. You can take up the better part of a period doing that. Just maybe go through one section of one chapter. And then there will be associated problems bundled with the ebook in an interactive mode, so that I hope I'm not over speaking it, but I do believe, I know in the physics book they have something called Learning Catalytics, which I believe is interactive, much like Khan Academy and IXL are, such that in a series of questions, whatever you get for the next question depends on your performance on the previous question, as opposed to just a straight set of questions, none of which depend on your how well you answered the previous one. So it's more like, let's say, having Socrates as your teacher, because he would ask a question, and then what he would ask next would depend on how you responded to the first question. So that is also very valuable. So just when you start the class, you can start with some of these essential questions. Students can have a notebook, write in the notebook, and make a discussion out of it. What factors determine the physical state of a substance? That means, for example, water can be in a solid form, ice, or a liquid form, or it can be as an invisible vapor. What determines which? Some students will say, obviously, it's temperature, but that's because they have spent most of their life in normal conditions. But pressure is also a factor that they don't consider, because the ambient pressure doesn't really vary appreciably or noticeably. So there's more to discuss in these questions than is immediately apparent. So just however you as the teacher decide to arrange it. In a period, I might start out with some questions and then go through the book somewhat with them, and then show them a video from Georgia Public Broadcasting. It covers basically the same area. Have them take notes while they're doing it. That right there is, you'd be very good to get even that much done in a period. And I just came up with that just off the top of my head, just doing this. You might have other ways to arrange the class. And once you have covered the material sufficiently, you're satisfied that they understand it based on looking over the sheets that they've done, the note sheets or the worksheets, then you can decide maybe we could do a very simple lab. They call them like a qualitative lab, something like that, where you don't have a lot of numbers and so on. It's not that rigorous mathematically at first. You're just trying to observe the phenomenon. So what would be an example of a lab? would be maybe you could there's something where you can heat up like a pop can with some water and then freeze it or put it in the freezer and then it'll collapse, something like that you could that it's like a prompt of what's happening there. And then as you've covered more of the material, you can have a more quantitative lab, which might take 3 days. You would study over the material, explain what you're going to do and what kind of data collection instruments do you need to prepare. Usually it'll be some sort of a table, and so you can create the table and then do the lab, and then you can analyze the lab. So it might take 3 days. If it's a short lab, you can analyze it that same day. Then you can show them some anecdotal thing. For example, here a video about Larry Walters. Larry Walters.
Atera includes everything MSPs and IT pros need in one.
This had been his dream for so long. Today was the day. He had spent weeks prepping and mapping out a route, and now bunches of helium-filled weather balloons floated overhead, tugging on the lawn chair. Larry strapped on his parachute and sat down. His ground crew watched, recording with a video camera. This was it. He cut the first rope and slowly rose to hover over the roof of the house. Perfect. Liftoff was progressing exactly like he'd planned. Suddenly, a strong gust of wind whipped past, rocking Larry and snapping the second line, tethering the lawn chair to the ground. Whoops! Larry shot up into the sky like he was being launched out of a cannon. Uh-oh, this wasn't part of the plan. Larry Walters had always dreamed of flying. At 13, he went to an Army-Navy surplus store and saw weather balloons on display. This inspired his idea of filling a bunch of weather balloons with helium, attaching them to a chair, and floating off into the sky. Unable to afford flight lessons, teenage Larry spent a lot of time hanging out at the local airport doing odd jobs. As a young man, Larry joined the Air Force, planning to become a pilot, but was rejected due to his poor eyesight. In the spring of 1982, 33-year-old Larry was living in Los Angeles, California, and working as a truck driver for a television commercial production company. He had never forgotten his weather balloon idea from some 20 years earlier. Now was the time to do it, he decided. Larry came up with a plan. He would launch from his girlfriend Carol Van Dusen's house in San Pedro, rise to an altitude of around 6,000 or 7,000 feet, drift northeast, heading over the San Gabriel Mountains, and eventually land in the Mojave Desert around 120 miles away. Larry and Carol spent over $4,000 to purchase 45 weather balloons, 55 helium tanks, a lawn chair, a CB radio set, and a BB pellet gun. To purchase the unusually large number of balloons and helium cylinders, Larry falsified documents from his employer saying the balloons were for a television commercial. During the planning stage, several weeks before his fateful trip, Larry's pal Ron Richland talked him into taking a skydiving class. After the class, Larry ended up buying a parachute. Though Carol and Ron tried to talk Larry out of what they felt was a dangerous, wacky plan many times, they agreed to be his flight crew. The night before his planned flight was spent inflating 42 8-foot weather balloons one by one. Around midnight, the curious police noticed the huge clusters of balloons hovering over the house and dropped by to inquire what was happening. Once again, Larry claimed they were preparing to shoot a commercial. Friday, July 2nd, 1982. Dawn's hot, sunny, and clear. Perfect for a balloon ride. Larry dubs his trusty lawn chair Inspiration 1. The weather balloons are tethered to the lawn chair with nylon cables in 6 tiers, rising almost 180 feet high. Over 21-gallon jugs of water are attached to either side of the lawn chair to serve as a ballast. There is no seatbelt, but the chair is positioned so Larry sits in it leaning back at an angle, making it hard to tip forward and fall out. The whole contraption is tethered to the ground via guide wires wrapped around Larry's Jeep. On board, Larry plans to carry several items to aid in his trip, including an altimeter, a compass, a 35mm camera, a BB gun, a map, and a small emergency kit. He even has some jerky, sandwiches, and a 2-liter bottle of Coke for snacks. Just before takeoff, Larry ends up delaying his flight by 45 minutes so his friend can go buy him a life jacket just in case he drifts near the ocean. Around 10:30 a.m., after putting on his parachute and getting comfortable comfortable in the chair, Larry cuts the first rope. He rises, hovering over the roof of Carol's house. Perfect. The first part of his plan is to float 100 feet over the house for half an hour, while his ground crew notifies the Federal Aviation Administration, or FAA, and local airports, and then drift off toward the mountains. But a sudden rush of wind prematurely snaps the second tether, jolting Larry and sending the lawn chair skyrocketing upward so fast, Larry's glasses slide off his face. Larry is ascending somewhere between 800 and 1,000 feet a minute. He contacts Carol on the CB and tells her that he lost his glasses. Nearly hysterical, she yells for him to come down, since he can't see. But Larry is prepared and has brought a second pair of glasses. He let Carol know and also tells her that he's headed into a small fog bank. Luckily, he comes through the other side without issue. As Larry rises, the view is fantastic. In the distance, over the houses, streets, and freeways, he can see the famed ship, the Queen Mary, at the port. As he continues to soar, he can see the curve of the California coastline, the Pacific Ocean, and then eventually Catalina Island in the distance. He watches a private plane fly past beneath him. He enjoys the view, but forgets to take pictures. In fact, for the duration of his voyage, Larry totally forgets to use his camera. To put in perspective how quickly Larry is ascending, in less than a minute, Larry has reached 500 feet and officially entered into federal airspace. In less than 2 minutes, Larry has risen higher than the 1,250-foot Empire State Building. In about 10 minutes, he's almost at 10,000 feet, or 1/3.
And so that's an example of anecdotal episode that bears upon the subject of gas and gas pressure, gas volume. It's a true story. It happened around 1980 out in California. So you can have a discussion about buoyancy and what do you think about his idea and what would you do differently. And I mentioned, I've told you that I can't really go through the ebook because they're doing maintenance on it and they'll be doing it until tomorrow night. But I mentioned there's a companion that several companion videos that you can use in this unit. And here is one.
Check out our new series, Chemistry Matters, aligned to the latest Georgia science standards. Available now.
Yeah, and this is the older one that
Have you ever wondered why a helium-filled balloon suddenly shrinks when you carry it out into the cold air? Or why an aerosol can isn't supposed to be tossed into a fire? Did you know that weather balloons aren't fully inflated when they're released? It all has to do with gas, believe it or not. We're going to answer all of these questions in this unit as we study the characteristics of gases. But before we begin, I need to make sure you understand some basic principles behind the theory that ties together the work of several scientists and explains the behavior of gases.
In this lesson, you will describe the kinetic theory and use it to describe the behavior of gases. You will also describe the concept of pressure and the instruments and units used to measure pressure.
We've already discussed several scientific models in chemistry. By now, you should understand that a good model in science both should explain the facts we know and be able to correctly predict events that are yet to occur. The model used to predict the behavior of gases is the kinetic theory that was developed in the mid-1800s. A gas that conforms to all of the assumptions of the kinetic theory is referred to as an ideal gas, which is imaginary, as opposed to real gases, such as hydrogen, nitrogen, oxygen, and others, which are not imaginary. A real gas behaves essentially as an ideal gas, unless the temperature is very low or the pressure is very high. Under normal circumstances, you can assume that a real gas behaves as an ideal gas. You need to get some of this information down in your notes.
The kinetic theory explains the molecules are so far apart that the total volume of the molecules is very, very